Okay, welcome to part 3 of our lecture for Friday, March 3rd, where we discuss the idea of formal charge and how that relates to our topic of resonance structures, which are all equally valid Lewis dot structures for a given compound. And when I say equally valid, I mean that we are able to fulfill all the octets and duets of the elements involved in the bonding of that molecule. So I've started here by making a statement, which is that not all resonance structures are equally stable. So if I were to be creating a Lewis dot structure of a particular covalent compound and found myself writing multiple versions of that Lewis dot structure, all with the octets met, they just look slightly different due to the placement of those double and triple bonds, then I would find that those different versions of that molecule, those different resonance structures, those different equally valid Lewis dot structures that I'd drawn, would not necessarily all be equally as stable or favorable, meaning that not all of them are going to be good representations of how I might actually encounter my molecule out in nature. In fact, the only time where we really see this idea of like equally stable resonance structures is when we've got quote unquote identical structures. So if we look at our carbonate example, right, notice that these three resonance structures are more or less the same molecule, right? This version 1, count correctly, is basically version 2 just rotated up, and version 2 is basically version 3 just rotated to the left. So since these are comparably quote unquote identical, I mean, they're not, they're different resonance structures, surely. Like, we do care that the top, left, and right oxygen are different. But if I were to look at these like without them being color coded or labeled, to me, these would all seem just like different representations of the same molecule. So in cases like carbonate, where we have a really large degree of symmetry, like that double bond is bouncing around between elements of the same type, then that's maybe a case where we might be able to say that our resonance structures are all equally stable. But that's not always the case, right? It's not always the case that we have these perfectly beautiful symmetrical molecules like carbonate. So how could we identify which resonance structure is the most stable? Well, we do so by performing a calculation on each atom known as formal charge, where formal charge, Fc, on any atom is calculated as the number of valence electrons on the atom when it is unbounded or unbonded, minus the sum of the number of bonding pairs on the atom when it is bonded in this particular molecule, and the total number of non-bonding electrons on that atom when it is involved in the molecule. Now, the requirements for stability, like how can I use this calculation to tell me if a resonance structure is stable? So if formal charge is equal to 0 on each atom in a neutral molecule or compound, then we are stable. If our formal charges are close to 0 on each atom, meaning plus or minus like 1, then we are a little bit more stable. And if we're looking at a molecule or compound that has formal charges that are negative, that are placed on our more electronegative elements or atoms, then this will also be a more likely stable resonance structure. Now, in general, the sum of all the formal charges on each atom should be equal to the total charge on the molecule. So in the carbonate example, remember that's a polyatomic ion that overall had a charge of -2. So if I were to calculate the formal charge on the carbon and each of the 3 oxygens and all of those resonance structures, then I should find in each of those resonance structures that the formal charge from the carbon and 3 oxygens sums up to the overall charge on the molecule, which was -2. So let's do an example where I want us to determine the most stable Lewis dot structure for fulminic acid HCNO. All right. So let's do an example. And as always, we are now calculating our number of valence electrons. We need to figure out our budget. For our bonding, so useful to have a little periodic table up here. So hydrogen, this is in the first column. This contributes 1 valence electron. Then we have 1 carbon, which is in the 1, 2, 3, 4th main group. So this contributes 4 electrons. Then we've got our nitrogen, which is in the group right after carbon, so it has 5 valence electrons. And then we have our oxygen, which is in the group after nitrogen, which has 6 valence electrons. So since I've got 1 of each of these elements, so hydrogen, carbon, nitrogen, oxygen, 1 of each, I need to just add up this total here. So that gives me 16 electrons that I have for my bonding budget. And now let's get started with our next step, which is to place all of our element symbols symmetrically around our centralmost atom. However, notice we've got an even number of elements here, or an even number of atoms here. So I'm just going to write these things in sequence. So let's just draw a line like H, C, N, O. Why not? Okay. Our next step is to connect all of our terminal or outermost atoms to our centralmost atom using single bonds. So here I'm going to link all of these together using single bonds. Now remember, each of these single covalent bonds is a bonding pair, or 2 electrons that are shared between these atoms. So 2, 4, 6. I have now used 6 electrons of my budget. That gives me 10 electrons left to play with. And our next step is to start filling in the octets for our outermost elements, starting with those that are more electronegative. So nicely for us, we've already got a ranking of electronegativity here. So oxygen, then nitrogen, then carbon, and then hydrogen. So let's fill in our oxygen first. So I've got 10 electrons. Oxygen currently has 2, so it needs 6 more to achieve octet. So that's 3 lone pairs. So I have used 6 electrons. This gives me 4 electrons left. And now I got to fill in for my nitrogen. So this currently has 2 single bonds. So that is 2 4 valence electrons. So I can add 5, 6, 7, 8. All right, let's ask ourselves if this is first and foremost a valid Lewis dot structure. So we got to check our octets. So here, just noting that I've busted my budget. I'm out of electrons. So if I were to look at my oxygen, 2, 4, 6, 8 valence electrons, that makes sense. I just forced that to have a full octet. Nitrogen, 2, 4, 6, 8 electrons. That has a full octet. Hydrogen has duet. But then carbon, 2, 4, has not met octet yet. So I'm not at the point of drawing resonance structures quite yet. I need to first and foremost just find a Lewis dot structure that is valid, where all the octets and duets are met in these atoms in this molecule. So I have a couple of options for how to do that. Let's see here. So since it looks like carbon is the one that is kind of lacking, it has the deficit, we could do something like, I don't know, let's start with this lone pair on nitrogen, convert it into a bonding pair to carbon. That gives us HC, which is now doubly bound to nitrogen, which is singly bound to oxygen. Let's see if that fixed our octet issue on carbon. 2, 4, 6, not quite. So I could take another lone pair on nitrogen and convert that into a bonding pair to carbon, forming then a triple bond between carbon and nitrogen, and a single bond between nitrogen and oxygen. Okay, let's count up everybody's duet and octets and see if this has led us to having a valid Lewis structure. All right, so I've got 2, 4, 6, 8 on the carbon, 2 on the hydrogen, so duet is met here. 2, 4, 6, 8. Octet is met here. Nitrogen, 2, 4, 6, 8. This has met octet. And oxygen, 2, 4, 6, 8. This has met octet. So this is one of our versions of this molecule that we could potentially draw, right? This is valid. This has all the octets and duets that are made. No big deal. Now, is this the only valid Lewis structure I could make from this molecule? So let's start playing around. Let's see if I can place my lone pairs and bonding pairs on different atoms so that we have different structures that are all equally valid. AKA, let's see if we can't find some resonance structures. So what were to happen if I were to take this lone pair on oxygen and make a double bond to nitrogen? Now you might be looking at that and saying, well, why? I mean, wouldn't this nitrogen not want that because it already had octet? And you would be absolutely right. If we were to force this oxygen to create a double bond to nitrogen, then there's no way that the nitrogen can retain its triple bond to carbon. So in this lone pair being the one that creates a double bond to nitrogen, we've got to get rid of those extra electrons somehow. So we're doing an unconversion, if you will. So we're not looking at a lone pair going into a bonding pair, but rather we're looking at a bonding pair pop out as a lone pair. So let's see if this is also valid. Like, let's see if messing around like this gives us something with all of our elements achieving octet. So I now have a double bond between nitrogen and carbon and a double bond between nitrogen and oxygen. And let's see if this is all right in terms of octet. So duet met on the hydrogen. I cannot give it a double or triple bond because this is an exception to octet. Looking at my carbon, 2, 4, 6, 8, this octet is met. Looking at my nitrogen, 2, 4, 6, 8, this octet is met. And looking at this oxygen, 2, 4, 6, 8, this octet is met. So this is another possible Lewis representation of my compound. Okay. Is there another way that I could do this? Let's find out. So looking around, like I've already kind of messed with my nitrogen lone pairs being moved and like the nitrogen bonding pairs even being moved. But yet I've only kind of looked at one option for my oxygen lone pairs being involved in forming these double and triple bonds. So if I were to take this lone pair on oxygen and convert that to a bonding pair between itself and nitrogen, then I need to figure out what would happen to my electrons on nitrogen to make sure that we're not, making something less stable. I'm still trying to achieve octet here. So notice in this version, this was a valid version of our Lewis dot structure because we had 2, 4, 6, 8 valence electrons on the nitrogen as well as oxygen and carbon. So if I were to try to convert this lone pair on oxygen into a bonding pair to nitrogen, this would give me a triple bond to nitrogen, 2, 4, 6, and then an excess of electrons due to that remaining double bond to carbon, 8, 10. So a similar idea is going to happen here. If I want my oxygen electrons to form another bonding pair to nitrogen, then in doing so, I'm going to have to displace a bonding pair as a lone pair off of nitrogen and onto carbon. So if I were to do that, then this bonding pair would have to move from the double bond between carbon and nitrogen onto carbon as a non-bonding pair or a lone pair. And so we would have something like this. So carbon now would have 2 lone pairs and would be singly bound to nitrogen, which itself would be now triply bound to oxygen, which would have only 1 remaining lone pair. And if we count up our valence electrons, so we've got duet on hydrogen, on carbon 2, 4, 6, 8, this is valid. On nitrogen 2, 4, 6, 8, octets met there. On oxygen 2, 4, 6, 8, we're good to go. Okay. Now, if I were to try to continue, like if I were to try to add this here, I would have to displace electrons here, which would displace electrons here, which would displace electrons onto hydrogen, which can't accept them. So I've kind of run out of options. Like you can keep going, you can keep trying, trial and error, but you'll quickly find that none of those give you any octets, or they break the duet. So I've now got 3 resonance structures for fulminic acid. I've got the one that is hydrogen bound to carbon, that is triply bound to nitrogen, which is singly bound to oxygen. I have the one where hydrogen is bound to carbon, which is doubly bound to nitrogen, which is doubly bound to oxygen. And then I have the version where carbon is singly bound to nitrogen, which in turn is then triply bound to oxygen. So these are my 3 versions from above, just written. again. And if I wanted to express these as resonance structures, I would use brackets and arrows to indicate so. So here's our resonance structures. Now the question is, which of these is the most stable, version 1, 2, or 3? And in order to answer that, we need to do our formal charge calculation. And unfortunately for us, we have to do a formal charge calculation on every atom in each resonance structure. So you'll find you'll get very fast at formal charge calculations because you'll be doing them so many times. So just a little reminder, formal charge is number of valence electrons. So I'm going to write that as VE minus the sum between our bonding pairs on that atom, BP, in other words, our lines, plus our non-bonding electrons on an atom, in other words, our dots. So let's look at version 1. And you know what? Let's go ahead and give us some space here. Not like that. That's not what I wanted. Okay, guess that's what we're doing. All right. So let's do our formal charge on the hydrogen. So hydrogen, when it is not bound, has a total number of valence electrons equal to 1. Minus the number of bonding pairs drawn to hydrogen, number of lines connecting on hydrogen, that is 1 line. Plus the number of non-bonding electrons on hydrogen. These are the dots found on hydrogen. We see that there are none here, so that's 0. So 1 minus 1 is 0. So here I'm going to write my formal charge on hydrogen as being 0, and I'm going to put it in a little circle, just to know exactly what charge goes where. And I don't want to confuse this for an ionic charge, so putting in a circle helps me make that difference or distinction. Okay, let's do the formal charge on our carbon atom. So carbon, when it is not bound to anything, has 4 valence electrons. And in this in this resonance structure, the number of bonding pairs or lines connecting a carbon is 4. And the number of dots or non-bonding electrons drawn on carbon is 0. So that gives us a formal charge of 0 on the carbon. Okay, formal charge on the nitrogen. So nitrogen, when it is not bonded to anything, has 5 valence electrons. And in this first valence structure, or resonance structure, excuse me, why do I keep saying that? We have, let's see here, how many lines connecting on nitrogen? So that's 1, 2, 3, 4. So we have 4 bonding pairs to nitrogen. And the number of dots drawn on nitrogen, number of non-bonding electrons is 0. So here, this would give us a formal charge of +1. And then formal charge on the oxygen. This has 6 valence electrons when it is not bonded to anything. And in this resonance structure, the number of bonding pairs on oxygen, the number of lines, is 1. And the number of non-bonding electrons, or dots, on oxygen is 1, 2, 3, 4, 5, 6. So 6 minus 6 plus 1, or 6 minus 7, is -1. All right, this is the formal charge assessment or calculations on my first resonance structure. Oh my God. What on earth happened? Why? Why, Notability, would you do that to me? Okay, let's see here. I'll briefly rewrite that. So while I'm rewriting this, why don't you get the jump on doing our formal charge calculations for version 2. All right, rewritten. So you are looking yourself at version 2. So I'm going to catch up with you. Version 2 is the resonance structure where we have hydrogen singly bound to carbon, which has a lone pair and a double bond to nitrogen, which itself in turn has another double bond to oxygen, which has 2 lone pairs. So let's calculate the formal charge on hydrogen. So hydrogen has 1 valence electron when it's not bonded to anything, minus the number of lines connecting on hydrogen, or the number of bonding pairs, which is 1, summed with the number of non-bonding electrons, or dots, found on hydrogen here, which is 0. So again, this gives us a formal charge of 0 on the hydrogen. Let's see how the formal charge on carbon might change as a result of this resonance structure being different. So carbon has 4 valence electrons when it is not bonded to anything. And I'm going to subtract from that the sum of the bonding pairs, or lines, that are drawn on carbon. So I've got 1, 2, 3 lines, or 1, 2, 3 bonding pairs on carbon. And I'm going to add to that the number of non-bonding electrons, or dots, that are drawn on carbon, which is 1, 2. So that is 4 minus 5. This is negative 1. So now the formal charge on carbon becomes negative 1, whereas before it was 0. Okay, let's do nitrogen. When nitrogen is not bound to anything, it has 5 valence electrons. And I'm going to subtract from that the sum of the number of bonding pairs, or lines, connecting to nitrogen. So that is 2, 4, 6, 8 total bonding electrons, or 1, 2, 3, 4 total bonding pairs, or 4 lines. And there are no dots, or lone electrons, or lone pairs, or non-bonding electrons drawn on nitrogen, so that is 0. So 5 minus 4 is plus 1. We have a positive charge on our nitrogen. And then for oxygen, this is 6 valence electrons when not bonded. And in this resonance structure, we have 2 bonding pairs, or 2 lines, connecting on oxygen, and 4 total non-bonding electrons, or 4 dots. So 6 minus the sum of 4 and 2 is 6. That gives us 0. 0 on here. That's the formal charge assessment on version 2. And now let's do version 3. This is a really long video. I'm sorry. Thanks for sticking it out. So HCN, triply bound to O. So my third resonance structure. Formal charge on hydrogen. Notice the hydrogen is this thing that is not changed in any of these resonance structures, right? It has just a single bond to it. So this formal charge is going to be 0 again. Carbon, though, this looks pretty different, so let's figure out what this formal charge is. That is 4 minus the sum of the 4 valence electrons, 4 valence electrons, minus the sum of the number of bonding pairs on carbon, which is the number of lines. So I have 2 bonding pairs on carbon in this resonance structure. And that is summed with the number of non-bonding electrons, or total number of dots on carbon, which is 1, 2, 3, 4. So 4 minus the sum of 4 and 2 is 6. That gives me -2. So that is the formal charge on carbon. And then the formal charge on nitrogen, that's its 5 valence electrons that nitrogen has when not bonded to anything. Subtract from that the sum of the number of lines drawn on nitrogen. So in this resonance structure, that is 1, 2, 3, 4 lines, or 4 bonding pairs. And the number of non-bonding electrons, there are none on nitrogen in this resonance structure. So that is, again, +1. And then formal charge on the oxygen, 6 valence electrons when not bonded to anything. Subtract from that the sum of the number of bonding pairs on oxygen, or the number of lines. So that is 1, 2, 3 bonding pairs, or 3 lines from that triple bond between oxygen and nitrogen. And this is summed with the number of non-bonding electrons, or dots, that are drawn on oxygen. There are 2. So this gives us a positive charge on oxygen. All right, let's look at our rules for how formal charge associates with air stability. So the resonance structure that has a formal charge equal to 0 on each atom should be stable. So let's go see if we can't find a resonance structure that has a maximum amount of formal charges that are 0. Okay, so hold on, let's see here, I think it's a little clearer, 0. So in this resonance structure, I have 2 atoms with 0 formal charges. In this middle one, I still have 2 atoms with 0 formal charges. But in this third one, I only have 1 atom with a 0 formal charge, so I can definitely rule out this last one as being the least stable. Okay. The next thing that'll give us an indication of stability from these formal charge calculations is if our formal charges are as close to 0 on each atom. So let's see if there's a distinction between how close our charges are to 0 on atoms in our 2 resonance structures. So here we had 2 0 charges, and then we had a +1 and a -1. So those are all pretty close to 0. And then in our second resonance structure, we had 2 0 formal charges, but then again a +1 and a -1. These are also pretty close to 0. So that was not really useful. It was not able to tell which of these 2 structures was the one that is more stable. Okay, the last thing we might look at is formal charges that are negative on electronegative atoms. Those are resonance structures that are stable. So we should have negative formal charges on things that are more electronegative. So in this compound or molecule, we would expect for that to be oxygen. So let's look here. All right, in this first structure, the oxygen gets the negative charge, the negative formal charge. So that looks promising. And you know what? In this second structure, the oxygen had the 0 charge, not the negative charge. So it seems to me like this guy here, which has the maximum amount of 0 formal charges and a negative formal charge placed on the electronegative atom, is going to be the most stable, with the next one, the next resonance structure, being somewhere in the middle, and then the least stable being the one that had our triple bond between nitrogen and oxygen. So let's go back to what this question asked us. Determine the most stable Lewis dot structure for fulminic acid. The most stable Lewis dot structure would be H, C triply bound to N, singly bound to oxygen, which has 3 lone pairs. This would be the most stable Lewis dot structure. In other words, the most stable resonance structure that I could draw. And I could only make that determination based on all of these formal charge calculations. Hoo boy. Okay, let's see here. Yeah, we are not going to talk about resonance hybrids or exceptions to octet today, so this will be a conversation that we save for Monday or even for our workshop on Tuesday. Because I've been talking a lot today. So I will see you guys in person on Tuesday, and then I will I will talk to you through your screen on Monday, the 6th. I hope we have a lovely weekend and that we're taking care of ourselves. And yeah, see you around.